Hello and welcome everyone. My name is Łukasz Argalski. I am Senior Software Engineer and Technical Lead at CodeLime. And today I have an opportunity to present to you the technical talk called Vector Databases. As you can see on Google Trends chart, the topic of vector databases granted significant traction since initial introduction of ChatGPT in November 2022. In this talk, we will uncover why exactly vectors and vector databases are needed in context of ML-powered applications. We will explore technologies sitting behind those, and we will see sample operational setup in action. Without further ado, let's start. Before going deep dive into vector databases, let's establish some baseline. Why exactly do we need vectors? One of primary uses of vectors in ML-powered applications are embeddings. Embedding is a numerical representation of piece of information. For example, text document, image, audio, etc. More formally, embedding is n-dimensional, dense vector computed from the input, from original input. The low-level details on how to calculate embeddings are outside of the scope of this talk. Nevertheless, it's still beneficial to understand what we can expect from embedding vectors in practical terms. Of course, output vectors are not random. From intuitive understanding, similar vectors are close to each other in n-dimensional space. Consequently, vastly different inputs will be far away in n-dimensional space. This property can be used to infer relationships between input data based on the relationships of vectors. Of course, this property holds if and only if all of the vectors were computed from the same ML model. Different models will produce different embedding space. This is the primary reason why we explore different models in the first place. And in general case, vectors from different models are not comparable to each other. Okay, so what is vector similarity? Vector similarity arises when we no longer have one vector, but we start analyzing two vectors. Formal closeness between them is indicated by distance metric. Very similar to distance in two-dimensional and three-dimensional case that we all know from our math classes in school. Distance in n dimensions is also well defined. As usual in mathematics, you can construct different metrics. You can see geometrical representations on the slide right now. The exact formula is not that important, but we have to understand that vector distance is computing single scalar value from two n-dimensional vectors. This will be a function of vector length and angle between those vectors. And very often, for popular embedding models nowadays, you will see vectors normalized to 1, which means that cosine similarity and dot product are functionally equivalent. So given two vectors, we can compute similarity metrics, and this similarity indicates how similar those vectors are between each other. Of course, this case is very simple. The idea of having two vectors is just naive edge case. Typically what happens is that you have many vectors, hundreds of thousands, millions of vectors, of vectorized entities, and you want to search for similar vectors, to vectors similar to your query vector. As you can imagine, for the relatively small entity set, naive search is possible, but at scale, we have to think about some indexing approach that will allow to search this big set efficiently. The state-of-the-art approach is HNSW, or Hierarchable Navigatable Small Words, and we will explore that technique in more depth right now. The basic premise of HNSW is as follows. If we can somehow avoid comparing vectors which are unlikely to produce high similarity scores, then hopefully we can provide results in near real-time fashion. To achieve that, we construct data structure consisting of layered undirected graphs. Topmost layer contains only a handful of nodes. Each layer below it contains more and more nodes with bottom layer containing all of them. In runtime, we start in topmost layer with arbitrary starting point called entry point. We run nearest neighbor search in this graph. This is very easy since graph is very small. Point that we found becomes entry point for layer below it, and then process continues. By reaching layer 0, we are already very close to our query vector, which means that local search, where most of the nodes are being disregarded, is good enough to produce accurate results. Not checking all candidate nodes, of course, can cause that we will miss some valid vectors, hence we are running approximated search. Nevertheless, this approach tends to produce high-quality matches, even for large search spaces. When working with HNSW index, you will be able to configure certain indexing parameters. These parameters will have very significant impact on functional and non-functional behavior of your database. Parameters both affect indexing time and actual search time. As you can see on the slide, 3 primary parameters are M, which is the number of neighbors for each node to be connected to in a graph. You have EF construction and EF search. Those are affecting how many nodes are, how many candidates are visited either during the indexing phase or during the search phase. As usual in engineering, there are certain rule of thumbs that we can follow. Of course, if we are keeping more edges in the graph, our index size will grow, index size and memory usage, but we can expect to have higher accuracy. For EF construction, more nodes to be traversed will cause higher indexing time, but once again, potentially higher accuracy. EF search applies the same principle, but during the search time. So with more nodes visited, we will have longer queries, but less chance to miss valid matches. Let's take a moment to do a quick primer on what we discussed today. We know that one of the major purposes of vectors in today ML applications is to construct embeddings, and embeddings capture semantic meaning of the inputs. We know that when pair of vectors is given, we can compute a similarity metric between those. The similarity metric is a scalar value, indicates how similar vectors are to each other. Vector search is a process of finding vectors similar to our query vector from the very large set of entities. And HNSW is a state-of-the-art index used to speed up those searches. Having this all established, the definition of vector database is fairly trivial. Vector database is a database which, first of all, allows you to store vector-like structures as part of the entity, and second, allows you to run effective vector search on stored entities. This is just it. As you can see, this definition is extremely vague, and I want to underline a couple of important things here. It does not imply at all whether a database is transactional, analytical, document-based, etc. It does not imply the deployment model, whether this is self-hosted or managed, whether this is single node database or distributed database. It does not imply how data is queried, whether you can use SQL or some other custom query language. And last but not least, in a simplest case, database itself is not machine learning enabled. It does not know about models being run within the application layer. All queries, inserts, updates are passing output vectors only. Summing up, the database being a vector database is not the only decision maker for you. And this explicitly omits very important criteria for database technology selection. And consequently, you do not have to use a new, shiny, dedicated vector technology to actually achieve vector database in production. And to prove that, I will discuss now a simple operational setup using two very popular open source technologies, which are not the first ones when you think about building a machine learning enabled solution. Those technologies are Postgres and Elasticsearch. First, we will prepare our test dataset, and we will vectorize it. And then we will showcase how to load and query data using Postgres with pgvector extension and Elasticsearch with dense vector data type and KNN search. For this example, I've used a dataset of 33,000 movies from Kaggle. It's important to underline that such datasets are very common for practicing building custom ML models, where typically you use handcrafted model features. This is not the case here. Here we will use movie's description and the generic text-to-vector model to run searches based purely on contextual meaning of English text. First of all, let's calculate the vectors of our dataset. Here, simple Python script is used, and inference is run on our local machine. At the very large scale, you may want to do batch processing in some big data cluster, or possibly run those on the GPU, but this is not essential for this demo. As mentioned previously, here as well, computation of embeddings is fully isolated from database. So we will compute those embeddings once, and then load those to both Postgres and Elastic. Let's start with Postgres case. Let's launch our Docker image with relevant pgvector extension already being part of the image. Let's create a table. Here you can see that extension is providing our custom data type called vector, and 384 is the size of output vector, and this is just property of the machine learning model used for the embeddings. Now we can run inserts to our database. We load our vectorized dataset. We set up standard connection using Python bindings, and we just run bulk insert into the database. This is very standard. First, let's try to run some random searches. You can see query on the slide. We can see that from the query and the results, we can see that our vector search is able to find contextual matches on our query, despite not having the exact match on query string used to compute query vector. Then let's create HNSW index. The parameters that you see on the slide, M and EF constructions, M and EF construction are fully complementary to the indexing parameters we discussed earlier. And let's run the same search. Here, Postgres Query Planner actually understands that there is a HNSW index behind, and it uses this index for this query, even though the query string hadn't changed at all. Keep in mind that we are running approximated search here. Therefore, by definition, we will achieve lower accuracy. In our test example, we can see results which are almost there, but we miss one of the movies from our top 10. As described earlier, this is due to the greedy search, where node containing this entity was pruned and not visited at all during graph traversal. Other than that, rest of the results looks very comparable. So for our use case, using the index does not introduce the significant recall penalty. For Elastic, we follow the same process. We start our instance. Once again, we start our Docker container using open source provided images. We declare our index. This is very, very standard Elasticsearch. Once again, you can see that type of the field is dense vector, and 384 is just property of the ML model used for this example. And once again, you can see M and UF construction, very similar to what we discussed earlier in Postgres case, and very similar to what we discussed earlier in HNSW theory. Then we can run our inserts. Very similar story. We load our vectorized data set. We bulk insert into our Elasticsearch instance, into our Elasticsearch index. Using Elastic, we can run naive search. Case of Elasticsearch is slightly different comparing to Postgres. We do not rely on any query planner. Instead, we have to run our queries explicitly. So here we run explicit query to compute naive cosine similarity against all documents in the index. For approximated search, we use KNN key from the query. So once again, here in Elastic, we are running custom query language, not SQL, but the approach is very similar. We are providing our query vector, we are providing which field we search for, and our parameters are complementary to runtime parameters we discussed earlier. In query response, we can see collected documents and value of cosine similarity stored in a score key, in a core field. So this concludes our example, and very natural question arises where we can actually use vector databases. And somewhat intuitive answer is everywhere where similarity or anomaly or pattern recognition is essential. So any recommendation engines, for example, we can consider things like B2B lead generation. In B2B lead generation, we are generating companies which are similar to some pattern that we established earlier. We can think about fraud detection, where we search for similar known fraudulent transactions which occurred in the past. Semantic search, as shown in today's talk, etc., etc., etc. What's important to underline is that, of course, business domains will vary. Embedding models will vary as well. For some of those problems, you can leverage quite generic open source models. For others, maybe you have to build your proprietary, very handcrafted ML model. You have to train and use it. Nevertheless, regardless of this context, vector databases is a tool that once you have your vectors, they will allow you to run effective searches against those vectors. Let's sum up. Embedding vector. Embedding vector is numerical representation of some data, which is designed to capture semantic meaning. Vector similarity is a scalar which indicates closeness of semantic meaning. Vector search is a process of finding nearest neighbors in a very large data set. HNSW is a state-of-the-art index used by many popular technologies. We also shown that sample operational setup on top of popular open source technologies, Postgres and Elasticsearch. Last but not least, let's address an elephant in the room. During the presentation, I claimed that you do not have to have a fancy vector database to run your approximated nearest neighbor searches. Yet in the market, you can find multiple offerings, and they advertise themselves as a best-in-class vector databases. So it's what exactly they do differently comparing to what we discussed today. And the shortest answer is that they do exactly the same thing. The essentials are exactly the same, but they deliver additional capabilities and additional value on top of these generic functionalities. The exact details varies from product to product, but things that are kind of popular, which can be found, is hybrid search. So maybe you want to run your vector query and post-process it somehow. Either add additional scoring on classical search methods, maybe re-rank to compensate for some behavior of your model, or to have tiebreaker, etc., etc. Some technologies are actually running ML models for you, especially if you're talking about kind of popular generic open source models, that you do not have to actually operate your machine learning model, and you can just ask your database to compute them for you. Some of the technologies had out-of-the-box support in their querying language for RAG, which is retrieval augmented generation, where the idea is that you are querying your vector database to find some context, and then you issue ML call. Then you issue a large language model call, for example, to ChatGPT, with your context to actually help it generate reasonable answer. Other technologies also, as we discussed earlier, we had a variety of parameters to HNSW. Some of the technologies are actually taking the responsibility of tuning those values for you so that the performance is reasonable without you actually setting them explicitly. Examples of technologies which are without particular order, you can see on the slide. So those solutions exist and they are valuable, but as I was saying, they are not needed for the they are not essential to have vector database in production. That's all I have for you today. I strongly recommend to you to visit codylime.com, where you can find other resources, including resources in data engineering and data science space. If you believe that Codylime can help you harness the power of vector databases, do not hesitate to contact us. My name is Łukasz Rogalski, and I hope you enjoyed this presentation. Thank you for your attention.